Fisher's linear discriminant. Fisher's linear discriminant or Fisher's discriminant analysis. This is a method used for binary classification via dimensionality reduction. That is, if you have data, let's say in two-dimensional plane, let's say all these are your data points. Using Fisher's discriminant analysis, you can project this data onto a line. That is, the two-dimensional data can be projected onto single dimension. That is, you're doing dimensionality reduction. Let's say this is your line to which you will project the whole data. So your complete data will be projected onto this line. So instead of all the points, now you will have all points on the line. Once you have it in single dimension, then it's easier to classify just by saying from this point, let's say this is the boundary. Before this boundary it is, let's say, class C1, and after this boundary it is class C2. So this is how you do classification using Fisher's linear discriminant. So this is achieved by solving an eigenvalue problem for the scatter matrices, and then we'll project it into the resulting discriminant axis. This is what we'll do. So we'll see in detail how this works. The goal is to find a linear combination of features that will separate two classes as much as possible. So here you have, let's say this is one feature is in y-axis and one feature is in x-axis. What we'll do, we'll find a linear combination of these features, let's say that comes in this axis, such that this axis is the best for the classification purpose. Then we'll project the data onto that axis and complete the classification task. Let us understand this in detail. So what we'll do is, first we'll understand it pictorially. From the graph we'll understand, so that the concept is very clear for you. And once the concept is clear for you, it gets stamped in your mind, we'll go to the mathematics behind and we'll solve how we can solve using Fisher's linear discriminant. Okay, let's first understand it from the graph. That will make it more easier. Moreover, you'll have an intuitive understanding, a logical understanding from this. Let us say you have two classes. Okay, so this is your axis and I'll say one class is, let's say, red. Okay, so in red class you have a lot of points here. All these points belong to the red class. Okay, all these belong to red class. You have one more set of points. These are in blue class. Okay, so this blue class, this is a different set of points. Okay, so let us say you have the blue class somewhere over here, maybe. Here you have the blue class. All these points belong to the blue class. So you have two classes here. One is the red class and the second one is the blue class. And your task is to identify which point is in which class. So you want to identify which points belong to the blue class and which points belong to the red class. So this is the task. Let us say you are trying to project it into one dimension and then you will try to solve this problem. How will you do this? Let us say you try to project it onto one dimension. Let us say your first attempt is to project it onto this x-axis. This is the x-axis. Let us say you try to project all the points down to the x-axis. What will happen? There will be, let's say, these red points. Let's say all these red points are projected and let's say they make all the points come here in this x-axis. Okay, all the points come down here. And you projected all the blue points here and all the blue points, they came down here. This is the present situation. But the problem is there is a small area over here where you see clear overlap of red and blue. So in this area, you won't be able to determine whether it is actually class red or is it class blue. If you try the same thing by projecting onto the y-axis, what will happen? All the points will be here. Red points will all be here and the blue points, they will all come here. There will be an overlap here because if you project these blue points onto here, there will be an overlap. So what happens now is, if you see, there is again a portion where you see an overlap of red and blue, which means you will again not be able to identify whether it belongs to blue class or red class. You won't be able to mark a boundary there. So what should you do? You should identify some particular axis if, to which if you project all the points, they will be clearly separated. Which axis will that be? Think of it. If you have, let's say, an axis like this, will it be separated? If you project it onto this axis, what will happen? All the red points will be projected here, all the blue points will be projected here, and everything will mix up. So you won't be able to separate at all. So that's not the right one. So which axis will give you the right solution? The answer is, if you have an axis which passes like this will give you the right solution, because if you project all the red points will be projected into the axis here. Everything will be projected here. And what about the blue points? All the blue points, they will be projected onto here. Right? This is where blue points will be projected. Which means if you say my decision boundary is, let's say, somewhere over here, then all the points on this axis which are to the right of this point, this will be in class blue. And all the points to the left, all these will be in class red. So if you project onto this axis, then you will be able to clearly say that one set of points are in class red and the other set is in class B. So this is how you have to do dimensionality reduction. You have to do dimensionality reduction by finding out the right axis. Reduce it onto that axis, which will give you the best separation between the classes. The next question is, how do you identify which axis has the best separation? How do you identify this mathematically? This is the whole task of Fisher's linear discriminant. Let us understand that. So if you want to identify that axis, this is how it goes. Let me erase this off. I'll just draw this axis again. Okay. So what qualities should be there for this axis so that it gets selected as the perfect axis to be selected in order to do classification? So I'll tell you the two qualities it should have. There are two qualities it should have. What is the first one? First one is that the between class variance of all the points, all the data points, when you choose this axis should be the maximum. What is variance? Variance is the spread of data. That is how well the data is spread. That is what variance will tell you. What is between class variance? Between class variance is if you have class 1 and class 2, between class variance will tell you how separated are the points of the one class from the other. That is, between class variance is very high if all the class 1 points are here and all the class 2 points are here. So here between class variance will be higher. What if all the points are mixed up? Let's say class 1 is like this and class 2 is like this. In this case, between class variance is lower because in a lot of places there is overlap between the two classes and the spread between the classes, that is lesser. So what you want is that you want between class variance to be as high as possible. For example, if you see this particular axis, when you project all these blue points and all these red points into the axis, what happens? The between class variance increases. It is the maximum if you choose this axis because you clearly see here is a boundary. All the blue points are towards the right side and all the red points are towards the left side. But if you choose some other axis, let's say you choose X axis to project and you project everything into it, between class variance is not so high. So first condition is between class variance should be the highest. And what is the second condition? First condition is between class variance should be the highest. Okay. And the second condition says within class variance should be the lowest. That is within class variance. It should be the lowest. What is within class variance? Within class variance means inside a class, how well is the data spread? That is if you have all these points belong to class blue. So in order to get the right axis, you want that the points of class blue should all be grouped together. You don't want that to be spread. You would ideally want that all the points of class red be grouped together, all the points of class blue to be grouped together, and they should be present in as lower a space, as small a space as possible. That is within class variance. So you want the within class variance to go as low as possible, and you want the between class variance to go as high as possible. So these are the two conditions we'll rely on. We'll keep a condition that we want between class variance to be as high as possible and within class variance to be as low as possible while we are selecting the axis. Okay, let's get into the mathematics behind and let's find how to determine that axis. Okay, so first we'll go through some basics that you need to understand so as to solve this problem. So the first thing is about the mean. Okay, so first thing is we'll compute the mean for each of the classes. So we have class 1 and class 2. First thing is, what is the mean for class 1? Mean is mu. Mean for class 1 is, let us say there are a total of n1 points in class 1 and a total of n2 points in class 2. So in that case, how can you, and each point will denote it as x. Okay, so all the points will be denoted as x. How will you find out the mean? The mean of class 1 will be 1 by n1 sigma x element of C1, which means for every x that belongs to class 1, you add it. So the average of all points, that is what mean is. So x by n1, that is your mean. Considering all the points in class 1, you add all the points and divide by total number of points. The same thing you will do for class 2. You will have mean 2, that is 1 by n2 into sigma x element of C2 x. So basically you are adding up all the points in that class and dividing it by the total number of points. So this will give you the mean. So you have mean of class 1, mean of class 2. So this is one basic, that is we'll use this in the derivation, mean of class 1 and mean of class 2. Second thing, let me erase this off. Next concept is of the scatter matrices. So scatter matrix is basically variance. So we'll call variance as scatter. Okay, scatter. So we'll find the scatter matrices for within class scatter and between class scatter. That is within class variance and between class variance. So let us start with within class. So scatter I'll call as S. SW is my within class scatter. So there are two classes here, class 1 and class 2. And within class scatter has to be calculated individually. That is, you can't calculate the whole scatter at once. You want to calculate the scatter, within class scatter of class 1. Then you have to identify within class scatter of class 2. So the total within class scatter will be a sum of both two. That is, within class scatter of class 1 plus within class scatter of class 2. And how do you identify this within class scatter? For any particular class Si, that is the within class scatter for the class I, can be determined as sigma x element of Ci, that is for every point that is there in class Ci. How will you find the variance? X minus mu I, mu is the mean, into x minus mu I the whole transpose. So this is how you find the scatter matrix. We already went through the variance lectures. So from the, you already know this thing, how to find the variance. So x minus mu I into x minus mu I transpose. This you have to find for class 1 and class 2. And then you have to add up to get the within class scatter. That is, for class 1, you will do S1 is equal to sigma x element of C1 and x minus mu 1 into x minus mu 1 the whole transpose. This is how you find the within class scatter for class 1. In the same manner, you will find within class scatter for class 2, and that will be your total within class scatter SW, S1 plus S2. So this is again something that we'll use in the derivation. So keep in mind, one is the mean of two classes. Mu1 is the mean of first class. Mu2 is the mean of second class. And the next concept that we introduce is within class scatter, that is SW. This is the within class scatter, total within class scatter. So we have two classes. The next concept is, this is the last one. After this, we are going to derive. So we have means, mean 1, mean 2, and then the within class scatter. The next thing is between class scatter, SB. This is the between class scatter. And how do you find this variance? That is the variance between classes. This is, mean is mu1 minus mu2 into mu1 minus mu2 the whole transpose. Sorry, mu2 transpose. So mu1 minus mu2 into mu1 minus mu2 transpose. This is the between class scatter. So you already know what is mu1, that is the mean of class 1, mu2, it is the mean of class 2, SW, which is S1 plus S2, which is the within class scatter matrix, and you also know SB, which is the between class scatter matrix. So all these data are of the points that we have. That is, we already said there are a set of blue points and a set of red points, and considering all these, we calculated mu1 of first class, mu2 of second class, within class, the total within class scatter matrix, and the between class scatter matrix. This is for the data that is provided. So till now, we all have all the prerequisites. Now we can go forward. So the next thing is, let us understand about projection and how should we project it. Okay. So let us say W is my projection vector. So I need a projection vector, right? That is, if these are the points, there should be a projection vector. So this one is a projection vector. So let us assume that my projection vector is W. Okay. W is my projection vector. My task is to identify what is this W. If I identify W, then the remaining is easy. I can project all the points onto W and I can classify. So the first thing, if I know W, how do I project all the points to W? Let us say I have a point X. How do I find the projection of the point X onto W? Very simple. It is Y is equal to W transpose X. This is how you project a point. If you have a point X and you want to find the projection of that point into a vector W, what will you do? You will do W transpose X. You have W, and W is the vector onto which you want to project, and X is the point which you want to project. So you have a point X and you want to project it onto some axis. So if W is that vector, W transpose X will give you the projection. So Y is equal to W transpose X. This is the projection of the point X onto W. Okay. So the next thing is, once you project, so whatever conditions we previously said, that is, one is that your within class variance should be the lowest, and the second thing is that the between class variance should be the highest. These two conditions are to be satisfied, not for the original points. See, for the original points, you already know what is the variance. These conditions are to be satisfied for the projection. That is, after you project onto this line, the vector, then these two conditions are to be satisfied. Don't think you have to satisfy it for the original points. For the original points, you already know it is given. Whatever is the within class variance, that is already there. Whatever is the between class variance, you already know. What do you want to do? You want to project it onto an axis, and you want to compare the within class and between class variance after projection. So after projection, you want between class variance to be highest and within class variance to be lowest. So our next task is to find all whatever we found previously with respect to the projection. So for example, we found the mean. We found the mean for one particular class and the other class. This time you want to find the mean for the projection. That is, if you are projecting this point, instead of mu1, you have, let's say, mu1 dash. This will be W transpose mu1. Why is it? Because you're projecting mu onto W. So when you project this mean mu onto W, it becomes a mu1 dash, which is W transpose mu1. Similarly, for the mu2, if you project onto W, you will get mu2 dash is equal to W transpose mu2. So now you have mu1 and mu2 as well as mu1 dash and mu2 dash. What are mu1 dash and mu2 dash? Mu1 dash is the projected mean. After you project it onto the axis, what is the mean of the data. Similarly, mu2 dash is after you project all the points of class 2 onto the axis, what is the mean? That is mu2 dash. So now you have mu1 dash and mu2 dash. The next thing is, previously we found the between class variance and we also found the within class variance. The same between class and within class variance you have to find after projection. So previously whatever we found SW and SB, right? SB was a between class variance and SW was a within class variance. We did S1 plus S2 and found the SW. But this SW was for the original points. What you want to actually find is for the projected points. After projection onto the axis, what is the SW within class variance? And after projecting to the axis, what is the SB, that is between class variance? These are the two things you want to find now. So let's find that. I'll write this here, mu1 dash is equal to W transpose into mu1 and mu2 dash is equal to W transpose into mu2. I'll write this here. We'll use this later. So next thing is between class variance. So like previously we put SB for scatter matrix. Let's use sigma. Okay, sigma B square. So sigma square is basically used for variance. Here it is between class variance. So I'm using sigma B square. Okay. How will you calculate sigma B square? That is the between class variance between the two classes after projection onto the axis. Okay. This can be calculated as mu1 dash minus mu2 dash the whole square. So instead of writing mu1 minus mu2 into mu1 minus mu2 whole transpose, I'm writing mu1 minus mu2 whole square. Okay. Now what is this mu1 dash and mu2 dash? We'll use this result. Okay. We'll substitute. So when we substitute, we will get W transpose mu1 minus W transpose mu2 the whole square. This is what you get. And when you solve this by taking W outside, you will get, I'm erasing these off, W transpose into mu1 minus mu2 into mu1 minus mu2 the whole transpose into W. Here, if you remember, mu1 minus mu2 into mu1 minus mu2 whole transpose, this was the exact value that we got for SB, the scatter matrix for between class variance. So instead of this, I can substitute SB here. So it will become W transpose SB W. So my between class variance for the points after projection, that is after projecting onto the axis, my between class variance, that can be written as W transpose SB W, where W is the vector to which I am projecting and SB is the between class variance before projection. So before projection, whatever was the between class variance of the points, that is my SB. And in a similar manner, if you solve, you will get for the within class variance, you will get sigma W square is equal to W transpose SW into W. Okay. So one is this, the second one is this. So the within class variance is this and between class variance is this. So now you know, after projecting onto the axis, within class variance sigma W square can be written as W transpose SW into W, and between class variance after projection can be written as sigma B square equal to W transpose SB into W. So now, what is our aim? You want to increase the between class variance as much as possible and you want to decrease the within class variance as much as possible. So this is what is called as Fisher's criterion. What is Fisher's criterion? So this whole concept of Fisher's linear discriminant, it comes from the Fisher's criterion. So what is Fisher's criterion? We'll call it J of W. Fisher's criterion is the ratio between class variance and within class variance. So it is sigma B square by sigma W square. This is the Fisher's criterion. Another way of expressing the same thing is I'll use these values. I'll use sigma b square's value and sigma w square's value. So it will become W transpose SB into W divided by W transpose SW into W. This is clear, right? So this is the Fisher's criterion. What is the next step? You want to maximize the value of Fisher's criterion as much as possible. And you want to see the value of W which will do this maximization. That is the vector W to which I have to project. As simple as that. See, if you want to identify which is the right vector to which you want to project, this is the vector. How do you identify this vector? You see the Fisher's criterion and you want to find the W which maximizes the Fisher's criterion, right? So let us see how to maximize this. In order to maximize this, it is very obvious that you want to try to increase the numerator and decrease the denominator. That is how you maximize anything. If you increase the numerator, it will maximize. Similarly, if you try to decrease the denominator, then also it will increase. But the problem is, what if denominator becomes 0? Then it is infinity. It should be very, very high value. But this should not be allowed, right? So in order to restrict this denominator from becoming 0, what will you do? We'll put a constraint that your denominator should be 1. So you'll say W transpose SW into W. This should be equal to 1. This is a constraint. Under this constraint, you want to maximize this value, the Fisher's criterion. So under the constraint that W transpose SW into W equal to 1, you want to maximize the Fisher's criterion such that you get the optimal W. So how do you normally maximize it? Under a constraint. This is where you use the Lagrangian. So this W transpose SWW equal to 1, this can be written as W transpose SWW minus 1 equal to 0. So I just took this 1 to the LHS, okay? So this is my constraint, and under that constraint I have to maximize this thing. So here this denominator, this is now effectively 1, so it is not important now. So what I'm trying to maximize is just the numerator now, because denominator is fixed as 1. So the numerator is W transpose SBW. Let us write the Lagrangian in order to maximize this numerator under the constraint that W transpose SWW minus 1 equal to 0. So the Lagrangian will look like this. Lagrangian of W lambda is equal to W transpose SBW. That is what you have to maximize. So W transpose SBW minus lambda into, you have to write the constraint, right? What is your constraint? W transpose SWW minus 1. So W transpose SWW minus 1. W minus 1. This is your constraint. Now what you have to do is that you have to maximize this Lagrangian. How do you find the maximum value? You differentiate it with respect to W. So you have to do del by del W of L W lambda, okay? Del by del W of L W lambda. When you do this, and you have to take the derivative and you have to equate it to 0. That's how you maximize everything. So you do a del by del W of this W transpose SB into W. If you do a del by del W, what will you get? You will get 2 times SBW, because this W transpose W, if you consider as W to W square, you will get 2 SBW after differentiation, minus lambda will stay as it is. W transpose SWW, what will you get? The 2 times SWW. This is what you get here, right? And this you have to equate to 0. When you equate this to 0, let me erase this off. What will you get now? If you remove 2 from both the sides, so from this equation I'm removing both the 2's. Now it will be SB into W minus lambda into SW into W. This is equal to 0. This is the equation that I get. If you take this thing to the RHS, you will get SB into W equal to lambda SW. And from here, if I take SW to the left hand side, what will I get? SW inverse SB into W is equal to lambda W. Now look at this equation very clearly. If you look at this, you will understand something. You will recall something. From the last lecture, what did we learn? We learned about eigenvalues and eigenvectors. Do you remember? So connecting to that, try to think about this. Connecting to eigenvalues and eigenvectors, try to think about this thing. What are you understanding from this? You will understand that if you take this matrix out, SW inverse SB, then W is an eigenvector of SW inverse SB and lambda is the eigenvalue of SW inverse SB, which means W is a vector to which if you apply this transformation SW inverse SB, W will not change direction and lambda will give you the extent to which W gets expanded. Okay, so here what is your aim? You want to find the optimal W. How can you find the optimal W? In order to find the optimal W, you want to find the eigenvector which corresponds to the maximum highest eigenvalue. That is, you have to find the possible values of lambda. That is, whatever are the eigenvalues of this matrix. You have to take the matrix SW inverse SB. You have to find the eigenvalues of that. And we already learned in the last lecture that corresponding to each of the eigenvalue, there will be eigenvector, right? So W is the eigenvector. So corresponding to the largest value of lambda among all the eigenvalues, whichever is the largest value, take the eigenvector corresponding to that largest value. That will be your solution. So the eigenvector of the matrix SW inverse SB, which corresponds to the largest eigenvalue, that is the axis to which you want to project. So this is how you find the axis to which you have to project. So using Fisher's linear discriminant, you had these points. You had these, let's say, red points here. And similarly, you had these blue points here. And you wanted to identify which is the right axis to which you have to project, right? That is what you wanted to find, which is the right axis to which you want to project all this data. And how did you find it? You found within matrix scatter, you found between class scatter, within class scatter, and from that you found SW inverse SB, and from that matrix you have to find the eigenvalues, and corresponding to the largest of those eigenvalues, find the eigenvector. That eigenvector will be this vector, which gives you the maximum between class scatter and minimum within class scatter. This is the axis to which you want to project all the points. If you project all the points here, then you can easily find a decision boundary, and you can say to one side of it, it is class C1, to the other side of it, it is class C2. So once you find this W, the only thing you have to do is project all the points onto this vector. How to project? We already discussed in the starting of this lecture. Just do W transpose X, then the point will be projected onto W. So project all points onto W and then do the classification. This is how you do classification using Fisher's linear discriminant.